So I will talk about my experience in porting Julia on the IPU. So the IPU is a accelerator kind of similar to the GPU, but it has some important differences. So here is a picture of a board of an IPU. So there are on each of these boards there are 4 IPUs, and each of them have about 1,500 cores. So for a total of almost 600 cores on the board. And each of these each of these IPUs have 900 megabytes of memory. So on the total of the board, you get 3.6 gigabytes, which is not a huge amount of memory if you're used to CPUs, but yeah, it's a kind of common in accelerators to have small amounts of memory. In terms of performance, each of these IPU deliver 1.4 petaflops, which is quite remarkable for like a single core like this. And yeah, so these are like the main technical details. And also, yeah, the memory speed is for the entire board is 260 terabytes per second. In terms of the parallel paradigm of the IPU, so the CPUs are like scalar in the smallest scale, like each core can do one operation at a time, but then you can have maybe multiple core to handle multi-threading. But ideally, each core is doing one operation at a time. GPUs instead are single instruction, multiple data, so they have a very large amount of cores that can run in parallel many operations. The caveat is that they can run a single instruction at a time on all the cores. So this is why it's called single instruction, multiple data. Instead, the IPU has a different paradigm, which is called multiple instructions, multiple data. So it's massively parallel because it can run completely different operations on each of these 1,500 core at the same time. So it's yeah, it's very powerful because you can have much more elaborate programs running on an IPU. And also forgot to mention that each of the cores of the IPU, which are called tiles, like in this picture, like each core is a tile of the IPU, can also have 6 threads. So for a total of almost 9,000 threads running in parallel on each IPU. So yeah, here is a comparison with a GPU NVIDIA 100, also like memory per core is like 100 kilobytes for the IPU and 7 kilobytes for the GPU. But the SIMD vector width is smaller because it's only 2 floats for the IPU instead is 32 floats for the NVIDIA 100. Programming the IPU. So the vendor of the IPU, which is called GraphCore, provides the low-level interface through a C++ library with which you can program you can write your program interfacing the IPU, but also the main use of the IPUs is for machine learning. So they provide the implementations of PyTorch and TensorFlow, which are aware of the IPU, and these are written in Python. But the point is, you can either use very low-level programming languages like C++ for interfacing the IPU, or use the domain-specific high-level tools that are provided by the vendor. At the moment, there are no way to do like generic programming using a high-level programming language. The way you write a program for the IPU, since I mentioned that you can run multiple instructions on each core, you can basically fed each of these core can run different operations and maybe using also different data, each of them. So basically the program, the IPU program that you write is basically a graph. It's also why the company is called GraphCore. And so yeah, you have these vertices which represent the operations that are being run on each of the cores that can get different data, and then maybe they will generate some data that will go into the next run of the operations running parallel on each of the core, which again can be in principle different on each of the cores. Very quick overview of how the Julia compiler works, but this is actually a generic compiler pipeline. So you write your source code in a file, then this is parsed, and you get a abstract syntax tree, which may be lowered into some typed AST, and then you generate an intermediate representation, which for the LLVM compiler is called LLVM IR. And then the Julia compiler runs some optimization passes, which changes every time the LLVM IR to generate some new IR until you get to the final intermediate representation, which is good enough for the Julia compiler to then generate the native code using the assembler. So this is how the Julia compiler works, or any compiler in general. And we used this pipeline to basically generate, maybe I can quickly go here to use the Poplar compiler, which is the compiler provided by the graphical company for generating code for the IPU. And the good thing for us is that also their compiler is based on LLVM. So what we're doing is to use the package called the GPU compiler in Julia, which at this point is a misnomer because it's being used also for stuff which is not strictly speaking a GPU. So you use this tool to generate the LLVM IR. We write it to a file and then use the Poplar compiler, so this POPC, to then generate basically a shared library which contains the IPU native code, and then we can run the code on the IPU. So we wrote this package called the IPU toolkit, which is on GitHub. It's also registered in the Julia registry, so you can install it as long as you have an IPU. And yeah, here is an example of computing, for example, pi using IPU. This is using actually a algorithm which is not very good for single precision, which is the largest floating point precision that you can use on the IPU natively. In fact, we will see the result is not very good, but this was an exercise for basically number crunching. So here we are calling the functionalities for setting up the IPU, distributing then the operations on all the cores. This is the kernel that we are defining to run on the IPU. Sorry, this one. And then, yeah, so the problem of the IPU is that writing code for the IPU is very verbose, and we are still not at the point yet where we can greatly simplify how you write it, but this is basically how you would write the same code on C++, literally pretty much the same in terms of verbosity, all the steps. But point is, we can run this in, actually, no, yes, here we can get a not too bad value of pi, even though already the fourth digit is wrong. And this took 0.12 seconds using this program written in Julia. And if we try to do the same with an equivalent program written in C++, here I'm showing only the kernel, which is pretty much identical to what was written in Julia. I'm not showing all the rest of setting up the program, so this is only the kernel. And if I run this, I get, yeah, the value is not very good, but again, the algorithm is very bad in a single precision. But the point is, performance is pretty much on par with the Julia. So for Julia was 0.12, here it is a 0.14. And if you're asking what's going on or for the difference, I believe the main difference comes from the fact that the Julia compiler is doing more advanced loop unrolling, because if you do manually, if you unroll the loop manually here, you recover basically the same performance as in Julia, also in C++. But the point of this comparison was to show that the Julia compiler can be a good front end for writing code for the IPU. An interesting feature of the IPU is that it supports stochastic rounding. So very quickly, this means that when you do operations involving floating point numbers, operations are not deterministically rounded to the same number every time, which is usually the nearest number in the set of the floating point numbers that you're using. But instead, you round your numbers with a certain probability, which, for example, for the IPU, if you enable the stochastic rounding mode, is this probability which is proportional to the distance of the number. So for example, if you do some more operations and your actual result is this x, instead of rounding deterministically always to x2, which is the closest of the adjacent numbers in the set of floating point numbers that you're using, instead of always rounding to this one, you round with a probability which is proportional to the distance between x and x2 or x and x1. So, statistically, you're rounding, if you repeat operations multiple times, you're rounding more likely to x2, but sometimes you also happen to round to x1. This stochastic rounding is very interesting because on average, it retains some information that you lose by using deterministic rounding, which introduces a bias, basically. And this is more important when you use low precision floating point numbers, like, for example, float 16 in Julia, the half precision floating point numbers. And there is an exercise that we can do here. So basically what I'm doing is to generate a vector of 3,000 times the floating point, the half precision floating point number 0.9, and then computing the sum multiple times using stochastic rounding enabled. So what we get is that using the nearest rounding, you will get this value, which is very much wrong because it's very far from the actual result, which will be 2,700. Sorry. Instead, with a stochastic rounding, you get this distribution, which is neatly centered around the actual result, which is to 2,700. And yeah, so it's not always the same result, but on average, you recover the actual result that instead is completely lost when you use nearest rounding. And yeah, so the cost that you're paying is introducing some stochasticity, but on the other hand, on average, you get much better results anyway. And we use this, for example, to solve a differential equation using the package called dfq gpu.jl, which again is a tool written for GPUs, but we can use the same technology also for running code on the IPU. I'm solving the Lotka-Volterra system. So like you can set up your differential equation in everybody's way to define ODEs, so using emojis. And then you write all this code. Again, it's very verbose. But the point is, we are comparing the result using double precision, which we take as the ground truth, which is in blue. In yellow, there is the half precision using the nearest rounding, which is the default way of rounding on the using the floating point numbers. And in green, you can see the stochastic rounding. So this is the solution of this differential equation. You can see that the nearest rounding is completely wrong in this case. Instead, with the stochastic rounding, we recover the precision that we lose by using a lower precision floating point numbers. But on the other hand, we are using 1/4 of the memory. So using low precision floating point numbers can be very useful for doing more operations in maybe less time or working on larger problems. Yeah, we can very quickly try different problems. So in other parameters, set of parameters of this differential equation, you can see nearest rounding is not that bad, but still stochastic rounding is much closer to the blue line, which is the double precision. We can also use automatic differentiation. So I don't remember if it has been mentioned these days that in Julia there is this package called Enzyme, which is a autodiff engine written actually in LLVM, so it works at the compiler level, and you can use it to generate the IR directly, the LLVM intermediate representation directly of the code that you want to, or the function that you want to differentiate through. So for example, here I'm asking Enzyme to generate the IR for the derivative of the sine function, and Enzyme spits directly the cosine function. And this is very important because on the IPU, it will be better to generate as much code as possible before running on the IPU, so at compile time. So Enzyme is very powerful in this case because again we can generate the exact derivative of our functions on the IPU. Sorry, on the host actually, on the before running on the IPU. And here I'm running, I will go very quickly, this is the Rosenbrock function, which is the standard example for optimization. And we are using a program which is using enzyme. We're writing a program which is using enzyme to minimize the Rosenbrock function on the IPU in parallel or using all the cores. Yeah, so for example, using this optimization method, which is based on the ADAM optimization method. Again, all the program, very verbose, but point is we can minimize on this grid of 33, almost 34,000 points in about 30 seconds using all these 1500 cores on the IPU. So it's relatively quick. On a CPU, this will take 10 minutes, I think. Like on a single core CPU will take over 10 minutes or 15 minutes the last time I tried. So yeah, you can see that by parallelizing your program, you can get a user speed up. Yeah, this is the IR. And so the summary is that this was actually the first time that someone was trying to use LLVM IR to generate code for the app using some other tools not provided by the GraphCore company. And yeah, I ran into some bugs, which was fun, but also it was a good experience. And but in general, I think the summary of this story is that the fact that Julia is based on LLVM is a great example of the fact that we can leverage LLVM capability of generating code and optimizing code for generating code also for new architectures that are not meant to be used by Julia or also are not supported actually by the vendor itself. Because yeah, this was a third-party effort from me and also some other people in the Simula Institute in Norway. So yeah, I think the takeaway message is that Julia can take advantage of the fact that it's based on LLVM for running also on these exotic architectures and generate also code which is fast actually. And yeah, this is it.